All right, so what is quantum lasso? Let's fix a state phi and define a function from Pauli to vectors. Define v of p to be p times to the state phi. And when you define the function v this way, it'll satisfy the constraints here. So if you inner product v of p and v of p, then it's 1. If you inner product v of pq and v of I, so it's not 1. It's same as v of p inner product v of q. Yeah, because Paulis are Hermitian, and yeah, so and the function is supported on exponentially big space. Now you can consider level k lasso, where you restrict the Paulis to be length k. You'll satisfy the both constraints, but now it's policized. Okay, now we can relax our original quantum X cup problem into this lasso. So write the objective function using the vectors v of i's, v of p's I just introduced. And these will satisfy some constraints. But if you're thinking in level k, the p's will be in length k space. The p's will be length k. But instead of considering actual the vectors I just defined, we could just see it as some vectors in a smaller space, so the dimension is polynomial. So yeah, in this paper, yeah, it's exactly momentum matrix. All right, so another important factor that we use in this paper is monogamy of entanglement. It's a quantum phenomena, and it gives a connection between quantum max cut and maximum matching. So consider this star graph, then the highest energy minus highest product state energy is always at most 1/2 on a star graph, regardless of the degree. So for example, if you consider just single edge, the highest energy is 1, but the highest product state energy is 1/2. So it saturates this inequalities actually. The energy is the objective function on single edge.
1 minus x.
Right, correct. And also notice that matching on star graph is less than 1. All right, so this is what I just said. And the key idea to connect maximum matching and our problem is that if you add these inequalities over the whole graph, then highest energy minus highest product energy is at most maximum fractional matching divided by 2 on the whole graph. So the question is, can we incorporate somehow this maximum fractional matching into quantum max cut? Okay, so maximum fractional matching and maximum matching are different, but of the constant, you could use one to upper bound or lower bound the other. So let's just say they're similar for now. So naive idea could be find the maximum matching. So in this case would be integer matching. assign optimal state, the single state, on the matched state, on the matched edge. Okay, this sounds good, but here are examples that doesn't work really well. So if it has high degree like this, if you assign single state on single edge, then it forces the rest of the edges to have energy 1/4. On the other hand, if you have the best product state, so for example, if you have 0 in the center and 1 on the leaves, then it has energy half on each edge. So if you add, then the product state has higher energy. All right, so here's our algorithm that's very simple and it actually works. So first, find the product state with high energy. Second, find the state based on the maximum matching. So I'll explain later what it means. And between 1 and 2, take the state with higher energy as the final answer. All right, so the first part comes from one of the previous work, the first work actually on this problem, European Parekh 19. So solve the level 2 Lasserre for our instance, and round some 3-dimensional version of Gomez-Williamson. So project a vector onto 3-dimensional space instead of 1-dimensional space, and normalize it, and use the final vector, 3-dimensional vector, to have a product state. And for the matching part, find the maximum integer matching. You can do this efficiently, and get the matching, and assign a product of 2 qubit states, which is a single state on matched edges, and uniformly random state on unmatched qubits. All right. Okay, I guess I have some time to talk about analysis. So that is the algorithm. So we use the standard SDP relaxation algorithm, which is that at the end we want to prove that the energy output by the state the algorithm outputs has at least alpha times SDP energy. So SDP objective value, where alpha is some constant. Okay, so because of this algorithm design, we'll have that the final energy is maximum of energy of the product state and energy of the matching state. And this is equal to maximum of convex combination of energy of the product state and energy of matching. All right, so the rest is just calculating each term. Product state energy is given by some similar process to the Gomez-Williamson, but now you need to do it in 3-dimensional, and that's done in Gaussian Parekh, and you get this hyperbolic function. And important thing is that you write it in inner products of this concatenation of phi of xi, phi of yi, and phi of zi. And the matching state is simpler. So if it's not matched, you get a quarter, and if it's matched, you get energy 1. So you can write it in this way. And yeah, we can lower bound the matching with SDP value because of monogamy of entanglement. And finally, just sum the two terms. And by taking the worst case of the Vi dot product Vj, you can get rid of the summation over edges, and you can just compute this closed form formula to get the ratio. Okay, so it's an open problem that I think is important, but our algorithm is classical, meaning that I give you this algorithm and say our algorithm outputs a state with energy 55. You can verify it with your classical computer. On the other hand, a quantum optimization algorithm, the energy can't be verified by a classical algorithm, but it could be verified by a quantum computer. So but we haven't found the quantum optimization algorithm yet. And yeah, as I said in the beginning, quantum PCP would give a hardness to quantum approximation algorithm. And ideally, we would like to find the optimal algorithm like Gomez-Williamson. All right, thank you.
Time for 5-minute questions.
Thanks for the great talk. I was wondering about your perspective on what you think about the 0.595 value. Do you think that's actually very close to the optimal we could ever get, or do you think like there could be a totally better way of rounding for this case?
I mean, I think there would be a constant difference, but I think we're pretty off. That's my guess. Yeah, because we don't even have a quantum algorithm yet.
I mean, even for the classical.
Oh. Yeah, I would still guess that there's.
Do you have any specific intuition?
Yeah.
Thank you for the.
Oops. Go ahead.
Thank you for the talk. I was going to ask, I might have missed this. What are you matching? I saw very quickly on the slide there was a definition, but what is the max match?
Oh,
here?
So maximum matching on graph theory is given a graph with weight, you want to find edges that doesn't overlap on a vertex that maximizes the weight.
Okay, so thank you for the talk. Indeed, my question was about if anyone has used tensor networks to solve this in practice. So I would assume that if your graph is random, maybe tensor networks are a very good algorithm. Has anyone studied this problem? I don't know, just try it out maybe.
It sounds like a great idea, but I haven't heard of anyone trying that.
Hi. So this area of quantum max cut, suppose that we get the best case scenario and we end up understanding, optimal approximation and whatever quantum algorithm for STP rounding. Suppose like it all goes, as well as we could hope. My question is, in the best case scenario, what do you think that would unlock in terms of understanding of quantum algorithms for relevant physical problems or?
Right. That's a great question. So maybe for that maybe to answer that, let's think about what's the difficulties we have currently to design such algorithm, right? I think the biggest obstacle is that we don't even have a quantum primitive for optimization algorithms. Like we don't have a quantum algorithm that outputs a state that has high energy. Maybe some local maximum algorithm that came out recently, but yeah, other than that, I don't know.
All right, looks like that's all the questions for now. Thanks so much. Next one will be at 2 p.m.
Maybe we can discuss later. Right?
Yeah, absolutely.
Yeah.
Thanks. What's the future?
Oh yeah, this is actually related to the thing. It's the dual of the semi-definite programming actually.
Interesting.
So yeah.
Hi.
Simple question. Quantum max cut problem, there is a max cut with the algorithm.
You mean classical method?
Yeah, classical max cut. Like many people I want to play with the quantum algorithm, for example.
Right. Yeah.
Is it another way to solve the classical max cut problem? Or is it different?
Okay. So I just need to wait here.
Yeah.
Okay. All right. I see.
When you're based at Tokyo.
Right. Yeah.
When does your talk start?
I think in 7 minutes or so.
Oh, okay, sure. I hope it's charged enough, but it
Oh,
should be
okay.
charged enough.
Okay.
I think it was showing that it was charged enough, but it just
Okay.
Do you need water or?
Okay. Yeah. Can I ask for water,
Yeah,
please?
sure. Yeah.
Thank you.
Just for this time, let me turn off this thing.
Yeah. Okay, we have this message.
All right, thanks everyone for coming. So I have Jun Takahashi here to present an SU2 symmetric semi-definite programming hierarchy for quantum max cut.
Thanks for the introduction. I'm Jun. Thanks for being here for the talk. And I thank the organizers for this nice opportunity. And this work was done in collaboration with Chaithanya, Rayudu, and Zhou from University of New Mexico, and Robbie King there from Caltech, and Kevin Thompson and Ojas Parekh. Ojas is over there from Sandia National Labs. And this was done while I was still at University of New Mexico. I recently moved to University of Tokyo, and here we go. So we already had a nice talk by Eunou Lee about quantum max cut. So I don't really need to introduce the computer science side of it, I guess, but I can still motivate why it's an interesting problem from the physics side, because I come from condensed matter physics background. So in condensed matter physics, this is known as the Heisenberg model, and it's actually used very often because it models a lot of different materials. And physicists are usually interested in the case where the underlying graph is a periodic structure, so some kind of a lattice, and you're usually interested in the thermodynamic limit, which means the infinite size limit and how the ground state converges to some kind of a phase of matter. And obviously the hardness of obtaining the ground state, or what it looks like, it depends on what kind of graph you're considering, and it's actually pretty easy to understand what the ground state is for the square lattice case. But once you introduce these, slightly more complicated lattices, it's actually up to this date controversial of in terms of what kind of ground state it actually holds. And for example, people don't understand if there is a quantum spin liquid state in these kind of models. And physicists do have, usual tools that they use in order to probe the ground states and thermal states of these models, namely quantum Monte Carlo and tensor networks. But they both have some shortcomings. They're not applicable to all kinds of materials. Or this has the sign problem. The tensor network doesn't really work well for higher dimensional systems. And we want to shed light into this problem. So physicists know empirically that this is a hard problem because they've been arguing for decades, but we have computational complexity theory in hand. So we want to see it from that point of view. So like already did, we can first look into the classical case, because in classical complexity theory, the same Hamiltonian without the XX and YY terms, so just the diagonal part, this becomes the max cut problem, or the antiferromagnetic Ising model. And for the max cut problem, we know very well that obtaining the ground state is NP hard, but the story doesn't end there. And we furthermore know that the celebrated Gomez-Williamson algorithm gives you an approximate ground state with this 87% approximation ratio. So that's really nice. But even nicer is that if you ask for anything epsilon better than this approximation ratio, then code proves that it is impossible to do that in polynomial time, assuming these p does not equal np and the unique gains conjecture. So there's a really clear threshold in the classical case at this 87% value. And the quantum Heisenberg model, you can view it as the quantum counterpart of this classical max cut, and that's why we call it the quantum max cut in this computer science context. We can exactly ask a natural question. So is there a similar phase transition-like behavior in terms of the hardness of approximation in the quantum case? But before asking this very fundamental question, we can already ask a more down-to-earth question. For example, how well does the semi-definite programming for the quantum case do? But before even asking this question, we can even ask a more down-to-earth question. What even is the quantum counterpart of the classically optimal SDP algorithm? Because once you get to the quantum case, you have this degree of freedom of different bases and stuff. So it's not even well defined, or it's not empirically clear a priori what is the natural semi-definite programming for the quantum case. So that's actually what we do in this work. So we come up with what we claim to be the most natural semi-definite programming semi-definite program for the Heisenberg model or the quantum max cut case, and we prove some good properties about it, and we also demonstrate and numerically observe that it also has more interesting features as well. So that's the pitch. And before getting into the details of what we do, I first want to quickly recap what the classical Gomans-Williamson optimal algorithm does. So the Hamiltonian looks like this for the classical case, Zi and Zij's. These are just plus and minus 1 observables. So with this convention, we have this strange 2 and 1 over it, just to make that each individual term is always 0 or 1. So that makes a nice convention. And in this convention, we can trivially have the upper bound of the energy that is exactly 0. And we know that the ground state energy, the minimum energy for this whole thing, should be minus m with some integer m. So now we know that the true ground state looks like this, plus and minus 1s. But what the SDP does actually is that it first gets a fake solution. So in general, I'm schematically drawing this like this. So, all the spins are not necessarily just plus or minus 1s anymore. It's some sort of a fake state. It's an unphysical state, but in that extended space of configurations that include these fake states, it's actually easier to obtain the minimal energy fake state within that extended subspace. That's the whole point of semi-definite programming. So, and the cool thing is that you can actually guarantee that this fake optimal solution is not so far away from this minus m. It's at most this % bigger. Now, the nice thing that Gomans and Williamson, found out is that from this fake solution, they were able to have a nice rounding, which is a way to project this fake state into a true plus and minus state. And because this was not so far away from the true value, they could also prove that this energy won't be too far away from the true ground state value. So this is what the classical Gomans and Williamson algorithm does. And Eunou's new result was mainly coming up with this nicer rounding and having a nice way to analyze their rounding scheme. What we're trying to do is come up with a nice semi-definite programming that does the first part. So what is the semi-definite programming really doing in the classical case? I first want to explain that using this example. So if you have 5 bits and a graph like this, the Hamiltonian looks like this, or the cost function looks like this. And let's say that you're encoding the true solution as a 5-dimensional vector with plus and minus 1s. So this is not a Hilbert space element. This is just a plus and minus 1 vector in 5D. But if you take the outer product of this, what you're going to get is what we call the moment matrix. So this moment matrix will encode all the correlations or moments up to degree 2. And the nice thing about this is that because of this construction, you can always guarantee that this has to be positive semi-definite, meaning that you never have a negative eigenvalue of this thing. And if you look at this moment matrix for a while, you notice that, hey, everything that comes into this cost function actually also shows up in this moment matrix. So you can turn this whole thing around and come up with a semi-definite programming problem, meaning that you want to minimize. So sorry, I'm just getting rid of this minus sign and writing maximize just to save space here. But anyway, you want to minimize the summation of these elements in your matrix that has to be positive semi-definite. And this basically corresponds to some sort of a similar optimization problem to the original problem. And you should notice, you can notice that the diagonal elements here are all 1s because it originally corresponds to things like zi squared. And zi's have to be plus and minus 1s in the original problem, so they have to square to 1, and we're taking that into account. And in the true moment matrix, everything, because everyone is plus or minus 1, everything has to be plus or minus 1 basically, but we're not imposing that here because imposing that will make this optimization problem very hard to solve. But if we allow any kind of real number here, then this whole thing is actually polynomial time computable. That's semi-definite programming. So we just run that, and hopefully, if everything is something like 0.9 or minus 0.8, if they're close to plus and minus ones, we can interpret this as some sort of a low energy state. And that's essentially what Gorman's and Williamson is doing. So, okay, we have this moment matrix. This moment matrix plays the central role in classical semi-definite programming. And if you look at this, you can notice that each rows and columns, they're labeled by ZIs. So from Z1 to Z5 in our example. And you can actually imagine a larger moment matrix that also contains rows and columns corresponding to higher order moments, like Z1, Z2 and stuff. And that will contain a more intricate or more fine-grained information about the state you're trying to get. So it corresponds to a better approximation. And that's exactly what this Lossar hierarchy is. And basically, if you contain everything, all the moments up to the kth degree or k body terms, that's called the kth level of the Lossar hierarchy. So in this case, because we only have one body terms as the labelings of rows and columns, it's the level 1 Lossar hierarchy. And people have been thinking about the quantum version of this. Basically, what you need to do is just say, okay, we're now regarding these labels, ZIs, as the Pauli ZIs. And we're going to have rows and columns also corresponding to X's and Y's. And also, that's going to be the level 1. So for level 2, we're going to have things like X1, Z2, and things like that, like these terms. And that's going to correspond to another quantum hierarchy, which is called the NPA hierarchy. And it's based on the Paulis. So people have been thinking about using this quantum NPA hierarchy for the quantum max cut, and people have gained nice bounds for the approximation ratio. But what I'm gonna explain now is that this hierarchy itself doesn't really suit the problem we are trying to tackle, actually. Or we have a more natural hierarchy. And okay, this is something already explained, so I'm just going to quickly go through. If you look at the quantum max cut, so again, we have this strange coefficient of 4 and 1, just to make that the lowest and largest energy or eigenvalues are 0 and 1. So that means this is actually a projector, and it's a projector to this singlet state. So we're just going to write the singlet projector as Hij. And this singlet state is a maximally entangled state. So when you have a graph like this, it's already kind of non-trivial because this edge is saying that it wants a singlet here, and this edge wants a singlet there. But because of monogamy of entanglement, that can't happen simultaneously. So what ends up being the ground state is a superposition of these two states. And this leads to the non-trivialness of this problem, even when the graph is bipartite, because you can have these singlet pairs between these qubits that are not even connected directly with the on the graph, and a non-trivial coefficient. And I'm stressing this point because for bipartite graphs, in the classical case, you already have the problem becomes trivial. So the problem is non-trivial for the quantum case, even on bipartite graphs. That's one big difference in the quantum case. So in the quantum case, we can look into even simpler cases, which are the star graphs that we also talked about in the previous talk. And the thing is, the level 1 hierarchy for the quantum cases with Paulis, it fails to obtain these energies as well, which is not immediately super bad per se, but it does contrast very sharply with the classical case, because for the classical case, the case with bipartite graphs is not only trivial, it's also actually already exactly solvable using the SDP. So although semi-definite programming answers are supposed to be lower bounds of the true energy, for the classical cases with bipartite graphs, it already matches exactly with the true ground state energy. So level 1 classical Lossar hierarchy was already enough for these trivial cases, whereas for the quantum case, the level 1 Pauli does fail for even these most trivial cases. So that's one reason to believe the Pauli hierarchy is not really nice in terms of tackling the quantum maxit problem. So what we come up with in our work is we observe that the Hamiltonian here is actually SU2 symmetric. So we can actually come up with a moment matrix that simply uses these H values and their moments as the elementary degree of freedom. So the level 1 in this new hierarchy has all the one-body terms of Hij. So it's going to have H12, H13, etc. And for the level 2, it's going to have things like Hij, Hjk, etc. So this new hierarchy, what we show is that when you look at it, so one thing you notice is that previously, because you had Paulis, because all Paulis squared to 1, all the diagonals had to be 1 exactly. Now we have projectors, so that point becomes a little different. Because you have a projector, when you square it, it becomes itself. So meaning that now the constraint is going to look like, okay, this thing has to equal this thing because this is just the square of that. And we also have commuting terms when the subscripts don't have any overlaps. And we finally have this non-trivial relation between singlet projectors when they do have an overlap. And this also ends up being some sort of a linear relation between what you have in this moment matrix. So you can, again, put this into an STP format. And we can prove that all you need are these 3 relations in order to have convergence. Again, we can prove that when you have large enough, okay, sorry, I might have skipped this, but just like in the classical case, we can prove that when you go to high enough degree, the hierarchy converges to the true ground state value, which means that we can view even the level 1 as a first order approximation for a systematically better approximation family. So with this hierarchy, we can show that already at level 1, it gets all the weighted star graphs right. So in some sense, we can say that we reprove entanglement of monogamy of entanglement from the SDP point of view. And in order to do that, I'm not going to go through the proof, but it has a nice geometric reinterpretation, which I think is nice. And we also can prove exactness for some families of graphs, like the complete bipartite graphs. And the interesting case is when you have a complete graph, when you have all-to-all connected uniformly graph, then if the number of qubits is even, then we can prove that level 1 gets it exact. And for odd number of qubits, it always gives this 3/8 error for some reason, and which we can prove for level 1. And so there's a big difference in terms of parity for the complete graph case, which, okay, thanks. Okay, running out of time. So which brings us to the question of how it performs for general cases, like for example, we can look into the Heisenberg chain case, which is just a one-dimensional cycle. And here we can prove, so the nice thing about just looking at the semi-definite programming solution is that we can calculate all sorts of observables from the moment matrix, because although that's not a true state, it has information about all the correlations. So what we find is that the correlation function decays in the right way in the thermodynamic limit. So from a physics perspective, it's somehow capturing the C=1 conformal field theory exponent correctly, although it's not getting the exact solution. So it can capture some physics right. And if we go on to see cases where we have next nearest neighbor interactions, then if we plot the energy we get from SDP and the true energy, we even see this point where it gets the solution exactly correct. And this point actually corresponds to the point where it's called the Majumder-Gauss point, where we can compute by hand the exact ground state being this kind of state. So there's some connection between these things, and we can further calculate, go on to see what happens for these controversial cases and measure
these order parameters that physicists usually look into, and even get phase diagrams saying that this part is antiferromagnetic, this is valence bond solid state, this is the dimer state. And the coolest thing is that we even can observe with SDP solutions a place where none of the order parameters are non-zero, which means that we seem to be capturing quantum spin liquid states, which physicists are all looking into or searching for. And okay, I guess I'm running out of time. So yeah, I'll just briefly just mention that we can also show that this particular property of frustration freeness and that physicists call, what physicists call frustration freeness, and our SDP solvability actually exactly coincides. And we show that in our paper. And we can view our algorithm as a algorithmic way to detect those frustration-free models. And yeah, this is just another thing, quick glance at how we prove the convergence for finite levels. And basically it reduces to showing this kind of crazy formulas between the singlet projectors. And yeah, the hardest one was to prove this one, but once you prove this thing using only the three basic formulas we use in SDP, then we can prove that it converges to the correct thing. And yeah, here's the final slide, and thank you for your attention.
All right. Thanks so much. Questions?
Thanks for the talk. So these outer approximations are used sort of all over condensed matter and computational physics. The interesting thing to know is that when you have this smaller algebra for your SOS, how does that compare to the sort of attendant size Pauli algebra form? So like the equivalent NPA level.
Right.
Is it better or worse?
Yeah, thanks for the question. So this actually, I think, kind of almost exactly answers your question. So this is the demonstration for the cycle cases. So I'm plotting the energy versus system size here. The red thing is the true ground state energy. And I have two lines because the even and odd cases oscillate kind of bad. So I just draw two lines for even and odd cases. And you can see that the ground state energy estimates from using level 2 Pauli is definitely closer to the true value. That's the green line. It's closer to the red line than the blue line, which is the level 1 projector, singlet projector, our hierarchy. But the point is actually this green line stops here because the SDP program, although it's theoretically polynomial time, it's actually very much impractical. So you need to stop here. You can't do any system sizes larger than that. And that's actually even smaller than exact diagonalization. Whereas with our SDP, we can actually probe to much, much larger system sizes, which actually is the requirement in order to use it for anything like doing computational physics. So with the previous things, people weren't able to really do anything like computational physics at all. But our hierarchy allows you to do that.
I think a couple of years ago, Gil Raphael at Caltech had a local version of this where the algebra is just local sites instead of the entire algebra that spans the entire lattice.
Right,
and I think it also had very good performance. And
I
so
see.
that would save you here.
Right. I'm not sure if they had convergence proof, though.
I'm sure they did not.
Okay. Thanks.
Thank you for the talks. Just a question of maybe a clarification and question. So I understood that what you're doing is that you're replacing the Paulis, right, with some SU2 invariant algebra.
Yes.
Which are these single projectors, right?
Yes.
Okay, maybe actually following up on what was asked. So you can generate, right, any projector, I guess, starting from the n local ones, right? 1, 2, 2, 3, 3, 4, etc.
Right. That's enough to. So once you have a line, in principle, with the combinations of those and multiplying those, then you can get the different ones as well.
Okay, but here, I guess at level 1, you want to take all the different possible
Right.
Otherwise you have to, okay.
Yeah, I think even if you do it like starting from that and defining that as level 1, and then having next nearest neighbor connecting ones as level 2, etc., then eventually that kind of hierarchy should also converge to the right thing, I think. But yeah, that's simply not what we did here. And that would also not necessarily, like, it won't be as kind of potentially practical as our thing.
And maybe just a clarification. So did I understand correctly that you have a polynomial time algorithm to probably correct to compute, say, the correlation functions in SU2 invariant chains? Is it no?
Sorry, could you say that again?
So we have an SDP, right? So
yes,
we know we can solve it, but I guess what did you prove? I guess you proved that the level 1 was correct for certain observables, or?
Right. So what we prove here is that it's actually enough, or it gets exactly the correct answer for this family of graphs,
which includes the bipartite graphs.
Which includes the star graphs. So
Okay.
this is an even smaller subset of bipartite graphs. So
not even chain.
On the chain, we don't have that proof.
Okay.
So, or as a matter of fact, we know that it doesn't get it right, but it somehow gets the critical exponent, which is like one number that physicists care about. Yeah. It, at least numerically, we can see that it's kind of getting it right. So that's actually a big mystery here. In some sense, you can say that level 1 sum of squares or SDP is capable of capturing an approximate C equals 1 conformal field theory, but like, you know, that's just rephrasing this observation in some sense.
Just for this observable. Thank you.
Yeah.
I have one question. Would you mind expounding on this frustration-free?
Oh, yeah. Thank you. Yeah. Sorry, I should have timed my thing a bit better. So frustration-free models are, in physics, they're basically defined as models where the ground state is a simultaneous ground state of all the individual terms in the Hamiltonian. And this particular case with weights 1 and 2 are known to be that. But if you actually look at the ground state, that's not literally true, because I plus 1, that's something like this. This bond, for example, is not satisfied. But if you rewrite the Hamiltonian like this, now this whole thing with 3 terms is actually a projector into a specific thing. So, you know, frustration-free comes with a particular way of rearranging the terms. And it's not always very clear. So maybe just because a given Hamiltonian doesn't look like it's frustration-free, maybe there's a clever way to rearrange everything. But what we show basically is that using our algorithm, we can always detect if there is such a thing within some asterisk with some conditions. But
wait, so what's the asterisk?
So it's that this projector can be written as a low degree polynomial of singlet projectors, so these H's. So yeah, that degree exactly corresponds to the degree that we're using for the SDP. And right now we're just, you know, we just played around with level 1, and in principle you can go to level 2. So you can say, oh, this model is actually not frustration-free for level 1, but it becomes frustration-free for level 2. That kind of thing can happen. We can, in some sense, I think we can say that our algorithm lets you quantify how frustration-free a system is. And I think that's pretty cool. Thank you for the question.
All right, that's all the questions now. Thanks so much.
Thank you.
So let's start with the last session of today on track C. So we start with Dominic Barry that will talk about quantum simulation of solid state materials.
Good, thank you. So this work is essentially on the topic. Oh, okay. Okay, so this work is on the topic of how to make quantum computers do useful things. So here we're trying to simulate solid state materials, which can be used, say, for designing things like batteries. So this is the latest in a sequence of work on how to do these simulations more efficiently. And this time we're using pseudopotentials, which is the key word here. And this is work in collaboration with a lot of people, including group of Ryan Babbush, the Google Quantum AI, and also like to thank Nick Rubin, who's doing some of the work on the chemistry in this part. So, and do we have a, so we've got a lock on this thing it's showing. No, there we go. Now it's working. Okay. So this is, there's been a whole long sequence of work on improving complexity of quantum simulations. So on this page, we're looking at the second quantized versions using molecular orbitals. So the idea here is that you're trying to find some small set of orbitals to represent a chemical system more compactly. So you might have something which is quite a complicated molecule, but can be represented with only, say, 100 orbitals or so, which is quite a small number. But since the classical complexity of simulating this is going exponentially in the number of orbitals, that's going to be classically intractable. So the capital N that you see here, that's the number of orbitals. So there's been a whole sequence of successive works on the simulation complexity in quantum algorithms, starting with n to the 11 or n to the 9, and that's polynomial, but since it's such a large power, that's going to be intractable complexity on a quantum computer down to, say, n to the 3rd for our work on tensor hypercontraction. So a lot of this work is based on trying to give more compact representations of the Hamiltonian. So a major difficulty with these types of approaches is that because you're trying to work out these very clever orbitals, you have to work out some integrals to work out coefficients in the Hamiltonian. And these are all classically calculated in advance, and all this classically calculated data needs to be fed into the quantum algorithm. And approaches like factorization and tensor hypercontraction are being used to reduce the amount of data that's being fed in. But here we go. An alternative approach which can be used to avoid needing to feed in data is to use a simpler type of orbitals. So this is the plane waves approach. And we're particularly interested in the case where the orbitals are corresponding to electron momenta. Now, the advantage of this is that you get a potential which now has a very simple functional form. So you just have something like a 1 over k nu squared here in these weightings. And this means that instead of needing to feed in classical data, you can just essentially compute things on the fly inside the quantum algorithm. But the drawback is that to get a sufficient accuracy, you're actually needing to use a much larger number of orbitals. So you might be needing to use, say, 100 or 1,000 times more than the number of molecular orbitals you'd be using in the previous slide. And this means that if you are using the same sort of representation as in the previous slide, what we call the second quantized version, where each orbital is needing a qubit, that'd be a totally unmanageable amount of the qubits to use. So instead we use what's called first quantization, where we have a bunch of registers which are recording the occupied orbitals. So each of these registers is essentially corresponding to an electron momentum in our representation. Now, with this larger value of n, you can actually get, these much better scaling in n as well. So even though the n is larger, an into the 1/3 scaling is going to give you much better performance than the n to the third scaling with the smaller n before. But the difficulty with this is that it's not really taking advantage of active spaces like with the molecular orbitals. So the idea with the active space is if you have, say, an atom which has the core electrons and then some outer electrons, typically these core electrons, they're always going to be in that orbital. So you don't really need to simulate them. Yep. Ah, yes, good question. So the eta is the number of electrons. So we're generally trying to reduce the scaling with the eta as well, but it's typically going to be much smaller than n. And I'm going the correct way. So this is where we use the pseudopotentials. This is essentially to get the effect of these active spaces. So rather than just having the bare nuclei in the simulation, we're grouping inner electrons with the nucleus and then have an effective potential which is smoothing off the singularity of the nucleus. And this is not only softening the singularity at the core, it's also reducing the number of electrons that need to be simulated. So both of these are giving us an improvement in the complexity. But the challenge is that this is much harder to simulate because the functions are now harder. So we have much more complicated functions rather than just a 1/k nu squared. So the full version of this is looking something like this. So you have these weightings of k nu squared here in this representation, and you have things in this round brackets here, which you can think of as effectively like a unitary. So this is a bit like a linear combination of unitaries form of an operator, which we have very nice ways of simulating. So that's the original version of plane wave. So if you're going to pseudopotentials, you're getting something that looks like this. So you can see going from here to here, it's just this weighting that's changing. But the difficulty is that this is not just the only part of the pseudopotential. This is what's called the local pseudopotential. There's also a non-local pseudopotential as well. And you see here that this function has gone inside this sum now. So this is dependent on Q here, and this Q is going to correspond to an electron momentum. I should mention as well that I'm omitting a couple of sums to simplify things. So this is just a term for a single the register for an electron momentum and a single nucleus. So you're also going to have the sum over the electron registers and nuclei. So to give you a speed course in block encoding and linear combination of unitaries, so the idea is that, say, you have some target system, then imagine you have an ancilla. So the idea is, say you've given this Hamiltonian as a linear combination of these unitaries u nu with weights a w nu. The preparation is giving you this superposition with square roots of weights. You do a controlled unitary inverse prepare and project onto 0. what you're getting is that Hamiltonian applied to the target state. And another very important feature of this is that you have this divide by lambda here. This lambda is a sum of weights, sum of absolute values, and this is governing the complexity of the overall simulation. Now, you might be, say, trying to estimate eigenvalues, or you might be trying to do time-dependent evolution, but in either case, the complexity is going to be proportional to that lambda, so it's important to make that as small as you can. This divide by lambda is also accounting for the fact that this projection onto zero isn't deterministic. But in the actual simulation, we're not actually doing that. This is just an abstraction to understand a further procedure we're using to construct a quantum walk that we can use for the time evolution, which I don't have time to explain further, but this is the key thing that we're trying to do, is this block encoding of the unitary. So in the local pseudopotential case, we basically have this linear combination of unitaries, a form where you have this sum with weights like this, and essentially unitaries in brackets. So this prepare is giving you the square roots of these weights, and then for the unitary, you want a shift of the wave number by nu, and the nuclear position is coming into it in this phase factor here. But then when you're trying to deal with the non-local pseudopotential, you also need an amplitude which is changing according to the system state. So this is no longer a unitary thing. This is a bit like we're replacing this controlled unitary with some other non-unitary thing which also needs to be block encoded. So there's sort of this two layers of things which need a functional evaluation for the block encoding. So we're going to have a prepare which is giving us weights over nu, and another step which is giving us weights dependent on q. And what they try to do in the algorithm is to actually make this much simpler and bundle most of the complexity of preparing weights like this into this part with the non-local pseudopotential. So this is what our functions look like. So this is our local pseudopotential, and this is our non-local pseudopotential. So I've written it here in terms of these functions f tilde, and the f tildes are polynomials in K with an exponential. So the difficulties in this are coming about from that sum and from the exponential. So the general idea in simplifying the implementation of this is that for the sum, we're wanting to do a linear combination of unitaries style approach to implement it. So the idea there is that we have some control register that's prepared in a superposition over Li and J. So that's in addition to the superposition over nu. So what this means is that we only need to do function evaluation using sort of coherent arithmetic on the quantum processor. For the argument, we don't need to do an explicit sum. And the other feature of this is that, if you remember before, these f's, these are the only parts which have exponentials in them. And when we have products of f's, we can bundle the two exponentials together as well. So for everything that we're seeing in the sums, we only need one exponential. So in this block encoding, what we can do is compute what the argument of the exponential needs to be, and then we do this coherent evaluation of the exponential. So that's really the hardest function to evaluate here. Everything else is just additions and multiplications. Then for the exponential, what we have is a QROM interpolation. So QROM is something essentially, if you're thinking of having some register which is storing Z, so the Z here would be something where we're working out a 2 to the minus Z, which is just a slightly adjusted exponential. And for each value of Z, we want to output some data. So we have some nice circuits to do that. And then the data that's output is actually giving us information for each of these little segments here. So each of these segments is going to be a polynomial interpolation. So basically it's giving you the value of Z, and it's giving you say a slope and an intercept and a quadratic term for an interpolation between these points. And then that means that the overall complexity of this is just a QROM, which actually has quite a small cost. The number of Toffolies is just going like the number of points you see there, and then some multiplications and so forth for the polynomial. So this is what we get for a few interesting materials, and the key column here is on the right, which is costs for block encodings. So these are in terms of counting Toffolies. So you see here, there's a range of say 20,000 to 50,000, but for a lot of these, a lot of the cost is just for accessing the registers with the electron momenta. So what this is telling us is essentially we've optimized the evaluation of the pseudopotential functions as much as is reasonable to give the best performance. But then the other thing we need to look at is the values of the lambda. So if you remember before, this was what's governing the complexity, and this is coming from essentially block encoding something like the Hamiltonian divided by the lambda. And this is a bit like a sum over weights, but the other thing is that because we're needing to have this separate preparation over nu and amplitudes according to values of nu and electron momenta, that's actually going to be changing the values of lambda that we get. So the values of nu are prepared according to this scheme with nested boxes. So the nu is in this three-dimensional space, and essentially if you look at the inner nested boxes, you'd be preparing all the same weights for nu. Then if you look at this box, excluding that inner box, you're preparing the same weights for nu again. But the weights for nu have to be the maximum over the actual weights that we want. And then the value of lambda is going to correspond to that essentially sum over the maximum in there instead of the summing over the actual values. So that's actually boosting the values of lambda that we get for the pseudopotentials. So if we now look at the results for these materials, we're actually getting quite large values for the non-local pseudopotentials. This is the local pseudopotentials and then kinetic term and electron-electron potentials. So we have maybe, yeah, I'm 5 minutes, I'm running a little bit fast because I was originally planning for a 25-minute talk, and then they said, oh, you should do your talk in 20 minutes. Okay, so you can, if you look at sort of the tightest possible values of the lambdas that you could get here, if you were able to prepare the values, the function over nu perfectly, you could maybe save a factor of 10, but that would be a much more difficult calculation. So you would have to have some much more difficult calculations for nu, which would be increasing the Toffoli complexity of the block encoding as well. So here's the example for the battery cathodes, and this is comparing to another work that we did earlier using a different approach, and that's shown as these bars here for a couple of example materials. So the idea is that if you can simulate batteries, you can design them for, say, batteries without a cobalt, and the classical simulation of these things tends to be quite challenging and give some incorrect predictions. So in these cases, our Toffoli counts for our pseudopotential approach are actually quite a lot larger than what it was for our earlier approach. So this is suggesting, oh, well, maybe the pseudopotentials aren't doing so well, but the drawback here is these are actually requiring a whole lot of ancillars. So what these are doing is they're using sort of a similar approach to the molecular orbitals case that I was showing on the first slide, except taking advantage of symmetries to reduce the amount of data. But there's still a lot of classical data that needs to be fed in there. with a variation of the Curon that's a bit different than what I illustrated before. But this is using a whole lot of extra ancillas to reduce the Toffoli count. And the number of ancillas that you end up using there is about 75,000. And that is expected to be really not usable in an algorithm for a size of quantum computer that's foreseeable. So say you're doing things in the surface code and have 4,000 physical qubits per logical qubit, then that's asking for 300 million physical qubits, which is a bit too much, whereas this is going down to about just over 1,000 logical qubits, which is far more manageable with the pseudopotential case. But as well, like if we could make this implementation with the lambdas more efficient, then we could be possibly making the Toffoli counts here similar to what it was in this earlier scheme. Okay, so I'll wrap up there, and I'll quickly mention the archive paper. And thanks everybody. I'll open the floor for questions.
So I'm wondering if our system is not periodic,
Yep.
does this method still have advantage?
That's a good question. So it can be used for non-periodic systems, but it's tricky. So something that I skipped over a little bit because I realized that just before the talk that I had 5 minutes less than I had thought, was that the molecular orbitals case is really designed for molecules, whereas the plane wave case is more designed for periodic materials. So you can imagine also using it for non-periodic systems where, say, you have some sort of large box and effectively sort of periodic copies of the system which are far away enough from each other, they're not really affecting each other. But it's expected that's probably not quite as good as just directly using molecular orbitals.
But the scaling is still better, right? Like maybe the overhead is big, but
Yeah. So this is where sort of the trade-off between number of orbitals versus scaling with the number of orbitals comes in. So you can, in theory, have this n to the 1/3 scaling, which is better with the number of orbitals. But for practical systems, you might need so many more orbitals, and also you have that scaling with the number of electrons that it might end up actually giving you worse complexity.
thank you.
Thank you for the talk. This is really interesting work. So for the part of the quantum circuit that synthesizes the lambda values, those circuits involve a lot of small angular rotations, right? Small angle Z rotations. Is that correct? Like you're synthesizing these small angle rotations with T gates.
Not really. We're not really doing much in the way of small angle rotations. This is more sort of trying to get the correct amplitudes in there. So even if when we are doing small angle rotations, that's adding things into a phase gradient register. So then everything's quantified in terms of Toffolis.
So then what part of the circuit is yielding all the T gates?
Well, most of what we have is essentially coherent version of classical arithmetic. So you have things like additions and multiplications, and then we translate that into Toffolis.
That there's part of the circuit that is dominated by Toffolis, right? But is the entire circuit dominated? Is the entire quantum circuit, like its T-gate complexity comes from Toffolis, or are there parts of the quantum circuit?
So we have the Toffolis for essentially calculating these functions. We also have Toffolis which are being used to select these electron momentum registers, which is another thing which is a fairly important factor in the complexity, which I didn't have time to go into. And the only thing where we're really putting angles in is, if you remember, we had that e to the I factor with the a nuclear position. So that's a phase factor. But this is pretty negligible contribution to the complexity. So we're just calculating this thing coherently in the argument of the exponential, and then that's being used to add into a phase gradient register for the phase rotation.
I see. That's very interesting. So the vast majority of the cost comes exclusively from Toffoli kits.
Yeah.
I see. Very interesting.
Yeah.
Thank you very much.
So in interest of time, maybe we should keep the other questions offline. So let's thank Dominic again.
But I'm not sure. Maybe we should double check.
Yeah, I'll double check. Okay, so we have the second talk of the session, and we have Daniel França talking about efficient quantum Gibbs sampling.
All right. Thanks for the organizers for having the opportunity to speak here today. So this is joint work with Camby's Jose in Paris and Alvaro in Madrid. And first, probably you noticed that the title of the talk is different from the one on the program, and also from the archive paper. And this is because when we submitted the paper, full disclosure, there are two parts of it. The second part was wrong. So thanks to Anthony Chen for noticing our mistake. In the meantime, we had found a way to fix the proof, not getting exactly the same result we had before. I'm glad to talk about it later if you're interested. But kindly the PC members agreed to just consider the first half of our paper, which is hopefully correct in the submission, which I'm gonna talk about now. So yeah, that's why there's gonna miss. You're gonna probably miss half of the results from this paper. All right. So well, if you don't know what quantum Gibbs states are, they're gonna be the main actors or the protagonists of this talk. You know, you're just given some Hamiltonian age. And some inverse temperature beta, and you know, you might want to prepare these quantum states for many reasons. They appear in physics, let's say in statistical mechanics, but also in some quantum algorithms, say for machine learning, also for optimization and so on. So there are many reasons why you'd like to actually prepare these states. You know, formalization happens all over the place, right? And you'd expect that at least in some regimes, you should be able to simulate these Gibbs states efficiently with a quantum computer. However, we didn't have, or even in some regimes with a classical computer, in fact, but we didn't have like some sort of universal result saying that, you know, for these classes of Hamiltonians and these ranges of beta, you can actually prepare these states efficiently on a quantum computer. And this is precisely the topic of this work. And there's been a lot of activity since we put this out, and we're understanding how to prepare these quantum Gibbs states. I mean, our understanding is improving a lot over the last few months. So maybe one possible way you could think of preparing such quantum Gibbs states is to try to emulate how people, or one of the main methods people use to sample from these things classically, which are Markov chain Monte Carlo methods. So they work very well in practice. People use them all over the place. And in some regimes, you can actually prove that these algorithms work efficiently. And a big open question is, can we find quantum versions of such algorithms to actually prepare quantum Gibbs states, right? And there is a standard way of getting something which is, in some sense, an analog of a, let's say, Monte Carlo algorithm for quantum systems, which tries to mimic how we model formalization, which are Davis generators, where you assume you're given, so you're Hamiltonian, and then you write down some interaction between a BAF and your system with some jump operators, and this gives rise to a so-called quantum dynamical semigroup, which is the generator of your same quantum Markov chain, which is then guaranteed to converge to this Gibbs state if you pick this function here wisely, and the jump operators and so on. So this is like some sort of standard recipe to how to get some chain that will converge to the Gibbs state if you run it for long enough. Now, this was done in the 70s, so why aren't we too happy about this thing? So it has some very nice features. Why aren't we happy, right? It has convergence. It satisfies a quantum version of so-called detailed balance, which is a condition that not only tells you that the Gibbs state is the fixed point of this evolution, but also tells you that this map is Hermitian in a well-chosen scalar product. And this allows you to study the convergence of the Markov chain by doing linear algebra, which is something we all like. You can even argue that this comes from a physical process. So these are very nice properties of this Davis generator. However, there are some things we don't like too much about the Davis generator, which is the fact that the terms in this Lindbladian are very much non-local. So, if you look at the Metropolis algorithm, it's mostly based on local flips classically, right? And it requires a lot of precision and energy if you would actually want to implement this on a quantum computer. So it's kind of difficult to simulate these Davis generators. And the fact that the jumps are very non-local makes it difficult to analyze them and get rigorous results on, let's say, how long it takes to formalize for these Davis generators. And so in some sense, they do have this detailed balance like the classical Metropolis algorithm, but we're missing these other ingredients, right? And other people have sort of put forward proposals of how to do quantum versions of Metropolis, like for instance the quantum Metropolis by Temin. But again, the updates require some version of phase estimation, are very non-local. It's hard to analyze this algorithm. At least I don't know how to do it. And there are other works going in this direction. There's really a lot of literature, but they're mostly focusing on they only come with exponential guarantees, in the sense that we only know that it might take exponential time and system size to prepare Gibbs states with these samplers, even in the for high temperature Gibbs states. Now, there has been a recent paper where they construct a new family of Lindbladians. As I said, there's been a lot of activity in this corner of the literature. There have been some other constructions since. And what is nice about this first proposal is that the terms in this Lindbladian, they are not precisely local. So they're, even if you have, let's say, a local Hamiltonian on a 2D lattice, the jump operators will not be like strictly local, but they're quasi-local in the sense that they have some sort of tail. And they satisfy exact detailed balance, which is again great, because then we can do linear algebra to understand them. And they also give a recipe on how to efficiently implement these generators on a quantum computer. So if you show that these generators converge sufficiently fast, then you also get a quantum algorithm out of it. And yeah, so the question then is, of course, how fast does it converge? So if I know that I can implement this Lindblad evolution for some time t using these resources, which is coming from the paper by Chen et al. The question is, how large does t have to be so that rho, ETL rho, is close to the Gibbs state? This is usually referred to as the mixing time. And there are multiple techniques to control mixing times. But here we're going to focus on something called the spectral gap of L. And essentially, if you can show, which here I'm denoting by alpha L. And essentially, if you show that this spectral gap is larger than C, then you get that the trace distance between the output of the semigroup, irrespective of what the initial state was, and your Gibbs state here should be, sigma here should be understood as the Gibbs state, will be bounded by this. So, you just have to pick t to be some polynomial. And if C, for instance, is of constant order, and you can make the trace distance exponentially small. All right. So what we show in this paper first is that for a specific choice of jump operators, and actually you can just pick them as like 2-qubit Paulis, and you have a Hamiltonian age such that you have some sort of Lieb-Robinson bound. So essentially, this is a bound on how fast information propagates under time evolution with age, unitary time evolution. So, this is in particular satisfied for all, let's say, local Hamiltonians on a lattice. Then, as long as the inverse temperature is smaller than some threshold temperature, which is of constant order, then the spectral gap, this C here, is really of constant order. So this tells us that this Lindbladian of Chen et al. Gives you an efficient algorithm for all high temperature Gibbs states of, let's say, physical systems. Now, you might interject and say, oh, great, but I mean, high temperature, I mean, this is the kind of stuff I can do with my tensor networks or my whatever other classical simulation method. Who cares? I wouldn't want to see this as an application of quantum computing. And I agree. But why do I think it's still important? Well, because you could say the same thing about classical samplers, right? So for classical algorithms, people also try to show that they converge well or they work well for high temperatures, right? And I think this gives us confidence that they might also work well for more complicated distributions where it's maybe impossible to actually show that they work well. So if you want to convince me that you have a good candidate for how to sample from these Gibbs states at, let's say, lower temperatures, then you need to at least show that they work well for, let's say, product distributions, or then the next step, high temperature, right? So that's why I think this is still interesting. And as far as I know, before this work, again, there's been a lot of activity since. I'm going to comment on it later. We didn't have like these efficient algorithms for such a universal class. So how does the proof work? It actually goes back to like closed systems. So because of this detailed balance condition, we can actually map this Lindblad evolution to a Hamiltonian by consider some sort of purification of the system. And what is important is that the underlying space doesn't depend on the temperature beta. Okay, so we get this family of Hamiltonians that are defined on the same Hilbert space with some parameter beta, which encodes the temperature. And we have the property that the purified version of the Gibbs state is the ground state of this Hamiltonian. It's also frustration-free, and the energy is zero. Okay, and the nice thing about this Hamiltonian is that it has exponentially decaying interactions. Okay, so even it's not strictly local, but it has exponentially decaying interactions. And if you pick beta equals 0, then which would correspond to having the Gibbs state as the maximally mixed state, the corresponding semigroup you get is just some sort of local depolarizing channel. And for that one, you can easily compute the gap. Everything is very easy. So we know that for beta equals 0, the Lindbladian is very easy to work with. We know what the gap is. Now, we can also show that because the ground state is just a maximally mixed state, that it satisfies a thing called local topological order. And there are these very strong and nice results on the perturbation theory of the gap of such Hamiltonians by, for instance, Robbie, Hastings, and Michalakis, which allow us to say that we can perturb our Hamiltonian in some way and around beta equals 0 and still have a gap. Okay, so essentially by showing, making use of these very strong results, we are then able to perturb these Hamiltonians in terms of the temperature and get some finite range for which the gap is still of constant order. So that's essentially how our proof works. All right, now another thing people want to do with quantum Gibbs states is consider the so-called thermal field double states. So people tell me this has some connection to black holes, and I don't understand this at all. I already had a conversation about this in the morning. Someone told me there's a poster about it. I'm looking forward to learning a bit more about this. But anyways, people care about preparing purifications of Gibbs states as well. These are called thermal field doubles. As far as I know, there were also no, except for some limited classes, like ways to prepare these Gibbs states, these purified states in a more like generic way, say. Our work also immediately gives you an efficient quantum algorithm to do that. Namely, we can again look at these Hamiltonians we obtain by purifying by mapping the Lindbladians into these Hamiltonians, and it turns out that then we can do again a perturbation in beta equals 0 until the desired temperature. Do adiabatic preparation now, where we vary this parameter beta, and we can show that you can efficiently prepare the purification. So here the scaling is a bit worse. So for preparing the actual Gibbs state, we have exponential. We have a log dependency on the precision. If you want to do the purification, it's polynomial, but it's also polynomial time algorithm to prepare these purifications for a very generic class of Hamiltonians and some constant temperature. All right. And you know, the proof just uses the fact that we have this uniform bound on the gap, and then you just need to pick your favorite adiabatic theorem and plug in the estimates you get. All right, so this moves us to the conclusion. So again, I think this was one of the first results on the exact preparation of high temperature Gibbs states, and also the thermal field double state. And there are quite a few questions that come out of our work. So first, I mentioned that there is a way, like the Chen et al. Give a way of preparing these Lindbladians on a quantum computer, but they require fancy block encodings and things like that. So it would be interesting to see if there's a more, let's say, natural way of simulating these dynamics that require less quantum resources, say. Another question is that I showed you that essentially our algorithm works by, or our argument works by perturbing around the maximally mixed state, and we use the fact that, you know, there it's really easy to get a handle on what's going on, and you use the fact that it's these evolutions are quasi-local and have other nice properties. Can we extend this to perturbations around other states of interest? Another question I find really interesting is like, how well do these evolutions proposed by Chen, and now also these follow-up works by, for instance, the group of Lin, how well do these generators actually work in practice, also for lower temperatures, right? More applications of Gibbs states, of course, and maybe a bit more on question number 5, which is I said that there's a constant threshold for the temperature over which we know it's sufficient, but I didn't give you exact constants. And the reason I didn't give them is that I don't know them. There was another work by Teng and collaborators that also showed efficient preparation of Gibbs states at high temperature. But I can say that their threshold temperature is, worse than ours for high locality, because we can, even though I don't know the exact threshold temperature, I can tell you that it scales inverse linearly with the locality of the original Hamiltonian, and theirs scales quadratically. So at least if you allow for Hamiltonians acting on more and more particles, our threshold temperature will be better. But it would still be very nice to get constants to compare. And, oh, sorry. Oh, no. And moreover, this work showed many nice things we don't have. For instance, they showed that these high temperature Gibbs states are all separable. So an important question is our temperature range also covering Gibbs states which are actually entangled in some way? That would also be interesting. And just with my last 15 seconds just to let you know that we have quite a few postdoc positions available with both Kambiz and I, and if you're interested in working on this and Gibbs samplers or Gibbs states in general, just let me know. So yeah, thanks for the attention.
Questions? So you said that you don't know the constant, but is it close to 1, or like it should be very close to 1, or how?
I have no idea. So the reason, okay, maybe I can tell you why I don't know the constant. And the constant is that the reason is that we're using these results by Hastings and Michalakis, and they're very, it's very hard to extract things from there. So frankly, I have no idea, because there are quite a few steps in the proof where they show that there exists some universal constant such that blah, blah, blah. And we weren't able to determine those things. So frankly, I don't know. Yeah.
Hello, thanks for the talk. Quick question about, do we know about lower bounds on how quickly, in the sense that you showed an upper bound on the sampling.
Mm-hmm.
Do we know about lower bounds as well on these things?
Oh,
or
so,
like high enough temperature or something like that?
So like if you want to say that, beyond this temperature is very, yeah, so actually, yeah, so there's been a lot of work in this direction recently as well. I think that maybe a month ago, there was a paper by James Watson and someone else whose name I forgot, showing that, I forgot what the exact assumptions are, but they showed that under some complexity periodic assumptions, even some sampling above a certain threshold is hard. So there's some recent work in this direction. I can point you to the references.
Yeah, thanks for the talk. That was very nice. I'm just wondering, it seems like tacitly here, there's an assumption that this Davies process will eventually give you something that looks like a thermal state. I'm wondering what happens for Hamiltonians that have things like scars and that kind of thing. Like, does this approach just sort of break down if you have these kinds of artifacts, these eigenstates in the Hamiltonian that don't look like thermal states in a subsystem? Or is that not something that you've considered?
I'm not 100% sure I understood the question, but maybe just to say that like this is the only thing we need. So, as long as this holds, and this holds, for instance, for any Hamiltonian on a lattice or on a graph that is well behaved in some sense. It's even, you could have like exponentially decaying interactions and things like that. So I would say that for most Hamiltonians that are, let's say, physically motivated, then this assumption should be satisfied. So it should be pretty generic.
Thank you.
I think for the talk.
Mm-hmm.
Thanks for the talk. I'm just wondering about your, you have done by adiabatic, right?
Yes.
And I haven't seen your gap dependence of the convergence.
Right, because we show that the gap is constant.
Oh, it is a constant.
Yes, yes.
Yeah, okay, because you know that classically you can guarantee the convergence by the inverse of the gap, right?
Yeah.
And then for a fixed temperature. So the idea that for each temperature, we can then converge for that and then change the temperature with some perturbation maybe, and then prepare another Markovian operator and then get the convergence and so on. And you have the quantum part of that. It's really close to that. And the convergence is the inverse of the quadratic of the gap. So this is a kind of the quantum metropolis version of the metropolis and that can go for whatever temperature that you like it. And you can do also looking by adiabatic theorems, this approach.
Yes, yes, yeah. But as the gap is like independent of system size, you don't see a big difference there.
Yeah, thanks for the talk. And what I wonder is there are like many different works about above a certain temperature, shala, efficient.
Yes.
And like just to mention two others, like the recent one by Evan Teng and co-authors.
Yes.
And also like some older one by Martin Cleach about locality of temperature, where he has some sub-result about
sure.
decay of correlations above a certain temperature that blah, blah, blah. Are these results somehow all connected, or are there certain details in the statements / assumptions that strictly separate them in some sense?
Yeah, so I mean, very hard question to answer in a concise way. But let's put it this way. So, for instance, this great result by Martin you mentioned, for instance, is more about, let's say, computing, let's say, some local expectation value. Here, we're giving you the whole Gibbs state. So this gives you more power. You can, for instance, sample from it and things like that, right? So there are different notions of simulation, different notions of what you can do, yeah, I mean, for instance, one thing that the result by Martin and the Tang have in common is that they use, for instance, cluster expansion techniques or things related to that, which is not something we necessarily do here. So there are also some technical differences, but I'm glad to expand on that over the coffee break. Yeah.
So let's thank Daniel again.
Thank you.
I noticed there was a brown next to the part about the wormholes. Oh, is that dot brown?
I'll close and open again.
Oh, yeah, sorry.
Thanks. Yes, I already said what I Yes, also already stole one. I think like the trying to move like balance. Yes, everybody do. But yeah, you were waiting on. Yeah, the front is actually. You remove. No, but I want to do the. I want to do that either, and then other result. What do you want to do? You can I know what I mean. Who are you thinking? Still one, yeah, but it's yeah, this I'm not sure. Yeah, this one has to roll from yeah, but because what I mean, for example, this paper yeah. From my perspective, yeah. They're only about the first. Yeah. Yeah. The quantum state. Yeah, exactly. Yeah, I mean, I guess That's classic. There we go.
So let's move to the third talk of the session. So we have Dong An on multi-product Hamiltonian simulation with explicit commutator scaling.
Okay, perfect. Hey, thanks for the organizer and thanks for being here. So this is the joint work with Junaid Aftab, who is a math graduate student from University of Maryland, also Konstantina Trivisa, who is a math professor also from math department at UMD. So today's talk is about Hamiltonian simulation problem, so which is the problem of solving the dynamics, the real-time evolution of this Hamiltonian H. So basically, like in today's talk, we will assume this Hamiltonian H to be time independent. That is like we don't have any like time dependent driven term, but like in some case, of course, we can make this H to be time dependent. So it corresponds to a time dependent Hamiltonian simulation problem. Like in this talk, we will also assume the Hamiltonian can be decomposed or can be written as the summation of many simple Hamiltonians. So for example, like we have those H gamma to be Pauli operators, to be some local Hamiltonians, which we know how to compute the evolution operator exactly. So the quantum algorithms are aiming at implementing this time evolution operator e to the negative IHT. So this is like the setup of the time independent Hamiltonian simulation problem. I think like many of you are quite familiar with this. And the Hamiltonian simulation problem is probably like one of the most promising applications of quantum computers. So basically like there are already like many existing powerful and efficient quantum algorithms on that. So like very roughly speaking, so all the existing algorithms can be like roughly divided into two categories. So which is the product formula and so-called the post-product methods. So for the product formula, since we assume our Hamiltonian can be like it is the sum of many simple Hamiltonians, then like a natural idea is to simulate the entire time evolution operator by the product of the simple exponentials, this kind of like simple evolution operator. So for example, like in the first order product formula, we just use the Lee-Trotter formula and then like evolve each simple Hamiltonian up to the same time and take the product of all of these operators. So this is like a first order approximation. And of course, we can make this product formula to be more accurate. So for example, like we can make the entire formula to be more symmetric. That is like we evolve the dynamics from the first Hamiltonian to my final Hamiltonian up to a half time step. And then we go back forward from the last to the first for another half time step. And then like the entire formula will be more symmetric and it will have a better accuracy. So it's like a second order convergence. And of course, we can go even higher order by some kind of like Suzuki recursion or some other recursive approach. But there's like another categories of this kind of like post-product methods, which is something that is not the product of those simple Hamiltonians. So for example, like their method based on truncated Taylor, quantum signal processing, cubitization, or the recent quantum singular value transformation. So all of these post-product methods are trying to further improve the accuracy dependence in this kind of product formula because there's like a fundamental limitation of this of the accuracy that can be achieved by this product formula. So I will just have a comparison of these two existing categories of formulas in a more in a more specific way. That is like if we look at the query complexity of these two different methods. So when we talk about the query complexity, we usually care about three different parameters. That is like we care about the norm of the Hamiltonians, or in many cases, it is just like the system size, the number of qubits of the problem. And we also care about the time dependence, that is like how the query complexity depend on the overall simulation time, and of course, like the accuracy of the entire algorithm. So let's first take a look at this time and error dependence. So for the product formula, the time and error dependence they are not optimal actually. For example, like for a p-th order product formula, we have the time dependence to be something like t to the power 1 plus 1 over p, and this is like always super linear for a fixed order T, and actually it can be even worse. It's really because like we cannot improve this kind of order T to make it to be almost linear. It's really because as long as we are constructing higher and higher order product formula, we have to use exponentially many local exponential terms. So it will prevent us from really getting this kind of time scaling to almost linear. But also like for the error dependence, it is also like always polynomial in terms of this 1 over epsilon. Of course, we can make the degree of this polynomial to be as small as possible, but we can never really achieve a polylog scaling due to the same reason. And that is like the motivation of many of these kind of post-product methods. For example, like the optimal post-product formula, post-product method can really achieve a strictly linear scaling in terms of the time, and log 1 over epsilon in terms of the error. I think it will also be divided by some log factor, something like that. And those time and error dependence are optimal because there exists some lower bound saying that, okay, this linear in T and log 1 over epsilon is the best thing that we can do. So this is like the advantage of this post-product method, which can achieve optimal time and error dependence. But there is some kind of disadvantage of this post-product method, which is the norm dependence or the system size dependence. So it's really because like in many of the post-product method, we need some kind of block encoding structure. So basically like we usually have this kind of spectral norm dependence of my entire Hamiltonian. But like for the product formula, actually in a recent paper by Childs and collaborators, they show that they have this kind of commutator scalings. So the commutator is the the commutator scaling is like the commutators among all of those simple Hamiltonians H gamma. And we know that in many practical examples, we have some nice locality structure or some kind of like special structures among my Hamiltonians. So this commutator scaling can really exploit all of these special structures. So it can be much smaller than the entire spectral norm of the Hamiltonian. So that is like the advantage of this product formula. And it's very important advantage because this commutator scaling can have a usually can have much better dependence in terms of the system size or the number of qubits. And then now we can see like by this comparison, we see like a trade-off between this standard product formula and many of the post-product method. Then here comes like a very natural question is that can we really combine the best properties of these two different categories of the method? That is like, can we really have a quantum algorithm which can have this commutator scaling that explore the locality of my problem, as well as optimal or at least near optimal time and error dependence? And this is like the formula that the method that I would like to discuss in today's talk, which is exactly so-called the multi-product formula. So the idea of the multi-product formula is to use some lower order product formula, but we further do a linear interpolation or linear combination of many different formulas. So here is the multi-product formula. And basically like here, we start with this U2, which represents the standard second order product formula. And the idea is that if we want to like simulate up to time t, then we will choose a time step size that is much smaller than this t. It is like t divided by this integer k of j, and we will choose different values of this k of j. And then basically like for this kind of u2 to the power kj, it's just like a second order product formula with different time step sizes. And then we take the linear combination of all of these formulas, and this entire linear combination is so-called the multi-product formula. So why does this formula work, or why do we really expect this formula to combine all the best properties? It's really because, so first, for the commutator scaling, because like the entire formula is based on the product formula. So for the product formula, we know the commutator scaling. So of course, we would expect the entire formula also have some kind of commutator scaling. And of course, since here we are doing this kind of like interpolation idea, basically like we can carefully choose all of these coefficients to cancel all the low order error terms and try to make sure that it achieves a really high order convergence and then have some near optimal time and precision dependence. So that is our expectation. And of course, like for this formula to make it to be an algorithm, we need to discuss some implementation, but I will not discuss in details in today's talk. But basically, like we have a quantum version, which is based on LCU. I think Dominic introduced that in the first talk in today's session. And also we can do this linear combination in a hybrid fashion. So this multi-product formula is not a new method. It's not like newly introduced in our work. So it actually like it was first introduced to the quantum world in this paper by Childs and Webb on solving also on Hamiltonian simulation tasks. And there's like a recent work find some choices of these coefficients AJ and KJ to make sure that the entire formula can really achieve a high order convergence and stays well conditioned. So by well conditioned, it really refers to the fact that we can implement that formula efficiently. That is like the one norm of the coefficients are nicely bounded, something like that. And after that, there are several works on the theoretical analysis of the entire formula, but like before our work, there's still like a big gap between our expectation and the theoretical guarantee. And that is like before our work, so we don't really know a rigorous complexity estimate with all of the desired features. That is like we want the commutator scaling, we want this near optimal time and precision dependence. So basically, like roughly speaking, like before our work, we know a formula of this multi-product structure, and we have some expectation on this formula, and there's some like partial evidence showing that it has all of these features, but we never know this. We didn't really know this for sure from a theoretical perspective. And the main result of our work is to fix this gap. That is like we have now we really have a rigorous guarantee on the complexity estimate, and we have explicit scaling on those commutators. And here comes our main result. That is like we proved that for the multi-product formula based on the second order product formula that I just showed you in like maybe like in the previous slides. So the overall query complexity can be something like mu times t times polylog mu t over epsilon. So here, let us first look at the time and precision dependence. That is like, if we look at the time and precision dependence, something like almost linear in terms of t, and we have a polylog in terms of 1 over epsilon. So basically like for time and precision, it is already achieving this kind of a near optimal dependence up to some polylog factors. But like here's like another parameter, mu. So mu parameter is what we call the commutator scaling. And at this point, so mu only depends on the nested commutators of all of my simple Hamiltonians with terms larger than or equal to 3. So it's like those nested commutators with depths larger than or equal to 2, something like that. So basically, like the point is that mu only depends on the commutators. So if all of the Hamiltonians commute with each other, then this mu would just be 0. So there's no error in the entire formula. But like here, this mu can really explore the spatial structure of my Hamiltonians. So by this complexity analysis, we can really guarantee the both nice features that we would like, we were expecting for this multi-product formula. So let me talk a little bit more about this commutator scaling mu. So basically, like for this mu parameter, so this becomes a little bit technical. That is like this commutator is defined by another homogeneous commutator factor, which is what we call alpha commutator J. So for this alpha J, it's just like the scaling of nested commutators with J many Hamiltonians. So it's basically like we have H gamma 1 all the way to H gamma J. So there are like J many simple Hamiltonians, and we just like compute the summation of the spectral norm of all of these commutators. So this is like the homogeneous commutator scaling defined by this parameter alpha J. And our parameter mu is something like the superiorm of all of this homogeneous term, larger than or equal to some order. So for example, like here, what we have is that we have this alpha j kappa plus 1, and this kind of j kappa are some even numbers. So basically like here, the commutators that we are taking are nested commutators with term larger than or equal to 3. It's really because like those j are assuming to be even numbers, and then like we have this plus 1, something like that. So here's like, I'm just trying to explain like, yeah, we have this commutator scaling with number of terms larger than or equal to 3. And actually like this kind of mu parameter, there's like another, a little bit more intuitive explanation is that it kind of like describing the growth of my commutator with respect to the order. So how can we say that? It's really because like if we assume my homogeneous commutator scaling alpha j to be something like n to the power j, that is like a geometrically growing series, this n in many applications, it will just be the number of qubits. But let's just assume if we have this kind of growth, then basically we can compute this mu just to be this kind of number n. So it's just kind of like the ratio between the one order higher nested commutator divided by some lower order nested commutator. It's kind of like describing the growth of this commutator in terms of the depth. And I would like to also mention that this mu is exploring the commutator scaling, but even in the worst case, it is still better than, or it is at least no worse than the spectral norm dependence than the worst case. You can really prove that by directly bounding the commutator by the product of the spectral norm of each Hamiltonian, then like everything just like becomes something like the overall spectral norm of the original Hamiltonian, which means that the commutator scaling is indeed an improvement compared to the worst case, to the standard spectral norm dependence that was achieved by many post-product methods. So like now we can compare our second order based multi-product formula with this new complexity estimate with many previous algorithms. So here's like a very rough comparison with the existing algorithm. Basically, like we are comparing with the standard second order product formula. We are comparing with the pth order product formula and also like the best available post-product method. So basically, like if we look at the time and error dependence, so as we've already shown, the multi-product formula can achieve near optimal scaling. So if we compare with this optimal scaling, we have some polylog overhead, but it's just like some minor overhead. But if we really compare this multi-product formula with the standard product formula, we can have a polynomial improvement. Although like the degree of this improvement will become less significant as we increase the convergence order of the product formula. And if we look at the norm dependence, so basically like the post-product method does not have commutator scaling, but now for the product formula and the multi-product formula, we all have commutator scaling. However, those commutator scaling does not depend on the same parameter. Like for the second order product formula, we have a dependence on the homogeneous commutator scaling with number of terms 3. And for the pth order, we have this alpha p plus 1. And for our multi-product formula, it's like another parameter mu, which is taking the superior of many other terms. And here comes like a next question that is like, how can we really compare all of those commutator scalings? Like they are all commutator scalings, but there might be some like more favorable or nice favorable things. And in general, this is like hard to compare because like they are kind of like, if we don't really look at the specific structure of some example of my Hamiltonian, it's really hard to say. But like in some application, we can make a more concrete comparison. So for example, like I want to show you like one of the application, which is the power law interaction. So suppose that we have an n-qubit d-dimensional square lattice, and basically on that lattice, we are defining the Hamiltonian, which is the summation of many two local Hamiltonians. So for each this h of I and j, they are acting non-trivially on only two of this lattice or two of the qubits. And of course, we assume this power law decaying as like for this h of I and j, the norm is decaying something like 1 over the distance between I and j to the power alpha, something like that. And here we are assuming a very fast decaying, namely this alpha parameter would be larger than or equal to the dimension of my lattice. So in this example, we can really compute all the commutator scaling, and actually like the commutator scaling was computed in this nice paper on Troyer errors. But like here we can use that result and compute all of this query complexity. So for the time and error, it is the same as the general case. But if we look at the norm dependence in the best post-product method, we have this n to the 3 dependence, and in the multi-product formula, we only have this power to be 7 divided by 3. So this is like an improvement from the post-product method due to the commutator scaling. But now if we look at the product formula, which also has the commutator scaling, then we can see the second order based multi-product formula also has a better scaling than the standard second order product formula, which is like 7 divided 3 over like this 5 divided by 2. So it's like slightly better. And actually like the multi-product formula is matching the norm dependence if we take the order to be 3, something like that. But if we really consider the high order product formula, we still have a worse commutator scaling. So the reason is really because in the multi-product formula, we still have some low order dependence that is like our commutator scaling still depends on the the nested commutator with only 3 terms or something like that. So we can further improve that by changing the base sequence in the multi-product formula. So maybe I'll just like skip that part and I can discuss that offline. And here's like, I show you like one example here, but also like there are some other applications on like electronic structure, K-local Hamiltonians. Basically like as long as the product formula can be advantaged, the multi-product formula will provide a further improvement in terms of time and error. I'm gonna skip this kind of part, and here comes the summary. So in today's talk, our main result is basically like we show a rigorous complexity estimate of a previous method, which is this kind of multi-product formula, and we show that it can have explicit commutator scaling and near optimal time and precision dependence. And if we compare the multi-product formula with the previous method, then it can exponentially outperform the product formula in precision, and also like have a polynomially better scaling in terms of the system size. And with that, I would like to conclude and thank you for your attention.
Thanks for the talk, Dominic. I just wonder about the order of the polylog. Do you have an idea?
Oh, the order for the second order based multi-product formula is something like 4 or 5. It's like log 1 over epsilon to the power 4 or something like that.
Thanks for nice talk. I want to confirm that when you say for the Q capacity for the multi-product formula, so which query are you exactly considering? And so and also wonder why you can outperform the product formula on the precision from the maximally to the polylog.
Oh, I see. Yeah, that's a good point. Actually, like when we make the comparison, it was not like very fair because like I just mentioned this query complexity, but like actually for product formula and post-product formula, we are using actually different query models. So for the product formula and the multi-product formula, the query complexity is the number of the simple exponential terms that we are using, those kind of like a time evolution operator of each h of gamma. So that is the terms that we are counting. But for the post-product method, we are counting like a different a query model, which is usually like the block encoding of the entire Hamiltonian, something like that.
And sorry, I want to continue my question. So for example, if you say you in the multi-product formula, you consider the input as the block encoding of Hamiltonians, then usually, I mean, for the block encoding, it has a dependency, as let's say the alpha is about the spectral norm of the Hamiltonian, right? How you can improve towards the QSVT methods about how you can remove the spectral norm of the Hamiltonian dependency?
Actually, like for the multi-product formula, we are not using the block encoding thing. Like for the multi-product formula, because like the formula is constructed by the standard product formula, so we only need to like implement those time evolution operator for simple Hamiltonians. So like for multi-product formula, we will never use the block encoding structure. The block encoding structure is only used in many of the post-product method, like the singular value transformation or some quantization. I can explain that a little bit more. So it's like, like here, like the implementation is based on the LC-Eunou approach, but basically like what we will have is the block encoding of each entire unitary. So it is actually not a block encoding because like for product formula, if you know how to implement the simple exponential terms, then basically like you don't really need any extra axilla qubits. So it's just like this unitary itself. And then for the LC, you can just like implement the block encoding of the whole thing. But like when we count the query complexity, so we don't really use the block encoding for the input structure. So it's just the block encoding is just like the output of the entire formula.
And sorry, so quick confirm, is it UJ or U2 in this slide?
Oh, it's U2. So that is the important idea. It's like we are only using the low order product formula to achieve some high order precision.
I just had a question about what kind of KJ values you expect for these types of things.
Oh, like the KJ values would be polynomial in terms of the number of the terms that we are linear combining. So it's like the point is that this KJ is not very, very large. That is the meaning, also the meaning of so-called the well-conditioned formula.
Yeah. Would you have like numbers off the top of your head?
It's I think like for second, if you want to like, it's something like tens of something like that. It's 30s, 40s, something like that. I think like in one of the paper that I mentioned, maybe like in the paper by by Low and collaborators, they have a very nice table showing like all of these choice of the parameters k and aj. But like for those k, if I recall correctly, it's just like 30, 40, or I think the largest choice would be something like 100 or something like that. It's not very large.
Okay.
I hope it's not very large. I'm not sure if you have like a different opinion on that.
Yep, thanks.
If there's no further question, let's thank them again.
Thank you.
I guess.
start? Okay. So let's move on to the last talk of the session. So we have Itai Arad talking about area law for maximally mixed ground states of local Hamiltonians.
Okay, thank you. So this is a joint work with Raoul Jain from CCQT in Singapore and Ras Viranko from the Technion in Israel. And I'm going to talk about having area laws for maximally mixed states in ground spaces of gapped Hamiltonians. So since they don't have much time, let me just go straight to. That was not there. Okay. So let me just define the settings. So I'm considering a Hamiltonian system defined on a lattice, a d-dimensional lattice, with qubits of dimension small d. And we have a local Hamiltonian defined on them, k local Hamiltonian. I assume that the norm of the term is 1. And I denote by E0, E1, etc. the eigenvalues of H. These are the energies of it, and E0 is the ground energy, and H0 is the eigenspace of E0, which is all the ground states of H. And a major question that people ask, in particular in physics, is what is the entanglement structure of states in this eigenspace? What do we mean by that? So major question people ask is if I partition the system into two parts, L and the rest of the system, how much entanglement do I have between these two parts? And to quantify that, one useful quantity would be the mutual information. So this is the well-known formula for mutual information. And I can ask, okay, for a typical ground state in such a system, how much entanglement or how much mutual information I have across the system. And the idea is that in physics, when we are talking about physical Hamiltonian, then many times in the ground state, because the ground state itself is a ground state of a Hamiltonian that has a short-range correlation, short-range interaction. These interactions, in some sense, many times when we go to the ground state, create only short-range correlations. And as a result, I'm hand-waving a lot, there is a short-range entanglement between different parts of the system, and therefore the entanglement in some sense is proportional to the boundary of the region on which we look. And this is manifested in the text that the mutual information will scale as the size of the boundary and not as the boundary itself, unlike, for example, random states where it will scale like the volume. So this is called an area law, and this is called a volume law. And it is a well-known conjecture in physics that if we look at ground states of gapped, of local Hamiltonians with a gap, this is a spectral gap. So we assume that the difference between the first energy and the ground energy is constant and does not decay as the size of the system increases. So once we have that, then it is conjectured that the area law is satisfied. Okay, so previous results about trying to prove this conjecture. So we have like a full proof of this conjecture in 1D, and all these proofs are for the case where there is a unique ground state. So Hastings first proved it, and then we had work that kind of improved on Hastings results. And for 2D systems, we don't have a full proof yet. All the proof that we have are under additional assumptions, so there is a full list of these things. And in the case where we're not having a unique ground state, but we have several ground states in the ground space, then one thing that we know that in the cases where we have an area law in the 1D and 2D, then we have this type of result for the mutual information for all the ground states in the ground space. So we see that we have some dependency on the degeneracy of the ground space. The larger the ground space, then we don't expect that all of the guys sitting there will satisfy an area law, or they will satisfy an area law, but the quality will go down and down, and it will degrade. And you can even you can even have a very simple toy model that shows you that, in case that you have an exponential degeneracy, then really you will find some states there that don't have any error law. This is intuitive. Okay, so what are we trying to prove? We're trying to show that in the case where you have many ground states and you don't expect all of them to satisfy an area law, there is one particular state that will always satisfy an area law, and this is the maximally mixed state inside the ground space. Okay, so this is where what I'm going to show, or to claim that we showed, is that if you look at this state, then it will satisfy an area law regardless of the underlying degeneracy of the ground space. And the reason why this might be interesting is that, okay, this is first of all, this is the most natural state in the ground space. This is a function of the Hamiltonian. When t goes to 0, it is the limit of the Gibbs state. We heard about it like 2 talks ago. And we know that there is an area law for the Gibbs state in the mutual information for constant temperature, but this thing is for the temperature going to 0. And also, it might be relevant for cases where we don't really have a lot of degeneracy, but we have a lot of other low energy state that create like a continuum of excitations. Then it might be generalized to this case. And also, in the end, it is proportional to the projector of the ground space. And then it might be useful actually as a mathematical tool for proving the error law for higher dimensional systems. We can slice the system in parts, and then in each part we might be able to use this result as a structural lemma about the projector in that size. So it might be a useful tool for the future. Okay, so how much time do I have? Okay. So, so in the rest of the talk, what I want to do, I want to try to explain a little bit of the proof. The proof is technical, so I can't really explain it all, but I'll try to give you a background about the framework in which we prove it, and a formal statement of the result, and then some idea of how it goes. Okay, so the framework in which we use to prove it is called the AGSP framework. AGSP stands for Approximate Ground Space Projector. And this is an operator that approximates, as its name hints, the projector into the ground space. So it is an operator K that what it does, essentially, it takes any guy inside the ground space and it preserves it, just like the projector into it. But instead of killing everyone out that is perpendicular to the ground space, it just shrinks them, okay? So it shrinks them by some factor delta. Okay, that's why it's not an exact projector, it's just an approximate projector. But in turn, it might also have this structural property, which it does not create too much entanglement. I can write it down as a product, as a sum of D product operators, and therefore the Schmidt rank of this operator is limited by D, and if I apply it on some state, it does not increase the entanglement by too much, okay? And a good AGSP is an AGSP in which there is a favorable trade-off between these two guys, okay? So the product of D squared times delta is smaller than 1/2. And why is that important? It is important because we have a general result for cases where we have a unique ground state, and the general result says that if you manage somehow to construct a good AGSP, you manage to prove an area law. Okay, and the intuition is kind of simple. Okay, the intuition it comes from this lemma. It is the bootstrapping lemma. It says that if you have a good AGSP, then what it means that you have some product state with a large overlap with the ground state. And if you have a large overlap with the ground state, then you can start with this product state, apply the AGSP, not too many times because you're already kind of close to it, and then you will reach a very good approximation of the ground space. And since you did not do too many steps, you did not create too much entanglement, and therefore it means that the ground state has an area law. So that's more or less the philosophy of proving area laws using this framework. Okay, so using these frameworks, we were able to prove, we were able to construct good AGSP in 1D case and in 2D case under under extra conditions, and hence these results followed. Okay, so this is the AGSP framework that I'm going to use. The other technical ingredient that we're going to use is the maximal information, which is some sort of a measure to quantify the amount of information in quantum states. So to define it, let's recall what is the relative entropy. Relative entropy of the state is given by this formula, and it can be seen a little bit as a distance between rho and sigma. And using the relative entropy, we can define the mutual information of a state with respect to some bipartition of the system using this formula, and it can also be written as this expression as the minimum of overall the minimal distance according to this measure between all states and the product states according to a given partition. So this is the definition of the relative entropy. The maximal relative entropy is defined by this formula. What we are doing, we are given a state rho and another state sigma such that the support of rho is inside the support of sigma. We are looking for the minimal t such that rho is smaller than t times sigma. Okay, and once we have that, we take the log, and this is the d max. The intuition is that if we have this, if rho is only slightly, if we have to multiply just by 1 plus delta, then actually rho and sigma are pretty close to each other. So this is like a good some sort of a distance measure, and then using this relative entropy, we can define the maximal mutual information simply like we define it here. So it will be the best product state that we can get that will give us the minimal distance with respect to that measure. Okay, so this is the definition, and another slight definition that we have is the epsilon I max. The epsilon I max is the best thing that we can get if we are looking at a ball of size epsilon around rho. So what does it mean? It means that I have some sort of a bipartition of the system. I will look for anything which is close to rho where this I max with respect to that rho and that bipartition of the system will be minimal. Okay, that's the definition, and the idea is that because I max is a very non-continuous quantity, it's very hard to work with it analytically, and so that's why we introduced I max. And there is this fact here that relates I max to the well-known mutual information, and it says that it is upper bounded by this formula, and as a result, if I'm taking epsilon to be 1 over L, and I have a bound on I max, it will give me an upper bound on I. So this will be the way I would proceed. Okay, so now I can state the main result. The main result says that if we have a local Hamiltonian and we have some bipartition of this local Hamiltonian to L and the rest of the system, and suppose God has given us this nice AGSP with d squared times delta smaller than 1/2, then the epsilon maximal mutual information satisfies this bound. Okay, so it is bounded by log d of the d is the parameter of the AGSP plus this thing, and taking epsilon to be 1 over L, then immediately and using the previous continuity result, then give us straightforwardly an area law on the mutual information. Okay, so this is what we want to prove, and in some sense this is the equivalent of the bootstrapping lemma that we had before for the unique state. But this time it is for the maximally mixed state. Okay, and then in addition, okay, so if we plug the previous construction for the AGSP that we had for 1D and 2D, then we get area law for these cases where we have high degeneracy. And in addition, we can show that it also implies, and in 1D at least, an efficient tensor network representation of the MPO that represents the maximally mixed state. Okay, so the proof. So okay, I have like 5 minutes. All right, I'll try to give some hint of how the proof works. So let's try first a Postman bootstrapping idea. So recall that that Imax is given by this formula. So let us start by with the best product that we have. So call it sigma L and sigma L complement, and then T will be this thing. So we have this. Let's start by definition. We have this inequality, and now we can apply a good AGSP on both sides. We will get this thing, and this is not a normalized state, so we can now normalize it, taking out the trace, and we will have some normalized state here. And the idea is now that because K was an operator that does not create too much entanglement, and we applied it here on a product state, then this sigma hat will not have too many guys there. It will not have too much entanglement there, and as a result, it's not too hard to see that there is some product state that you take out of the expansion of sigma hat, and then you can upper bound it by some d squared time this product state, and altogether, if you plug it here, you will get this expression. Now we use the fact that we started from the guys that were already the best, the optimal, and we reached yet again another bound on the ground space with respect to some product state, and then this means that all of this expression here must be smaller than T because T was the optimal. So as a result, we get this inequality. We take off T and we get this thing, and now we can now work on what is written here. So we expand this product state. We expand it into a part which is in the ground space and a part that is perpendicular to the ground space, and taking the trace. Now, because this is an AGSP, then actually, if we have the ground space here, it can be absorbed into the projector, to the actual projector. So just have this. And here, since we are now perpendicular to the ground space and we are acting with K, so remember K, what it does when it hits something which is perpendicular to the ground space, it shrinks it by some delta. So altogether we get this expression, and now using the fact that d squared times delta is smaller than 1/2, after some simple algebra, we finally get that the overlap of this product state with the ground state projector is upper bounded by some constant that depends on d. So this is already a nice thing. It tells you that there is a product state that has a non-trivial overlap with the ground space projector, but it's not sufficient. It's not sufficient. First of all, we wanted a bound on T, but we got a bound on the overlap, which is I mean, and also the fact that we get some state that has a nice overlap with the ground space doesn't mean that it will give us in the end an area law for the maximally mixed state. Remember, we wanted the maximally mixed state. So if this guy is, for example, just a pure state, and we apply the AGSP on it, we will end up again in a pure state. I mean, it will be just the action of the ground space projector on this pure state, which will also give us a pure state. So this is definitely not the maximally mixed state. So this is not strong enough. And the idea that we have in order to overcome that is, but somehow what we wanted to do is to work with flat states. Now, flat states are a mixed state in which the weight of all of their eigenstates is equal. Okay, so these are in some sense proportional to projectors, and
if we had a flat state, if this sigma were flat state, then actually you can show that there is a simple relation between the Dmax and the overlap, and therefore, since we had a bound for the overlap, that will give us straight away a bound for Dmax. And the question is how to get that. And this is the second new ingredient in the proof, and we are using a technique pioneered by Raoul and Anwar, Jane and Anwar and Zhou, which is called the brother extension. And the idea of the brother extension is that you can take arbitrary states that are not flat, they have different eigenvalues, and then you extend it to an auxiliary Hilbert space in which they appear completely flat. And the way you do it is that, first of all, you assume that the eigenspaces are rationals, and if they are not, then you approximate it by something which is rational. And then, if you have one eigenstate that its size is, for example, 3/6, then it will appear appear as a tensor product with three guys in the brother space. Now, when you trace out the auxiliary space, you will get back this state. And then the idea is to somehow work with the proof in this state where everything is flat. And when everything is flat, there is a very natural connection between the overlap and the Imax. So this is the road that we follow, and I don't have time to go over it. But in the end, we apply a certain argument in an iterative manner. We always get some product states that are that satisfy this condition, and using the brother extension, we can relate their overlap with the ground space with their Imax, and in the end we get the result we need. Okay, so let me summarize here. So what we managed to accomplish is to find a bootstrapping lemma for the maximally mixed state in the ground state, provided that we have a good AGSP. It gives us automatically area laws for these highly degenerate cases in 1D and 2D. I mean, places where we already had such constructions of AGSP. It also gives an efficient tensor network representation in 1D at least, as an MPO. And some open question is there, first of all, for me personally, is there a simple proof? The proof is, in my taste, too complicated, and maybe there is some combinatorial proof that can be found. And then, we know that the Gibbs state, going back to the Gibbs state, we know that it has an area law if it is on a local lattice for any finite temperature, and this result shows it also has an area law for zero temperature. Then can we somehow will this imply that there is an area law all along the way? That's I think an interesting question. And the other thing, which is more technical, but maybe because actually what we are giving some structural property of the maximally mixed state, which is proportional to the projector on the ground space. So maybe we can use these properties to try and to in some sort of bootstrap the proof of the area law from 1D to 2D to 3D, etc. So this is it. Thank you.
Questions?
Thanks for the talk. So one question. So you said that you get an efficient MPO representation, but can you actually find it efficiently, or is it just like an existence result?
It's an existence result, but I suspect that in 1D, just like we have proof that in the unique case, you can also find this thing, the tensor network representation efficiently, then it should be also possible in this case. That's my guess.
I see, but there's no
no proof.
No, okay.
Can you comment a bit? Why do you think? Why do you think that it helps for having AGSPs in higher dimension? Like, what's?
Okay.
sorry. Yeah. So the thing is that, assume that you have this result in 1D and you're looking at the frustration-free case. So you might attempt to prove the area law in 2D by, you want to show that you have a bounded entanglement between this side and that side. So you might want to somehow construct an AGSP that has has low Schmidt rank between this side and that side. So this result kind of tells you, okay, look, you can take the projector on this row, the projector to the ground space on this on this row. You know that because it is a frustration-free Hamiltonian, then the degeneracy of this Hamiltonian here is exponential. But still, if you look at the projector here, then because of what we proved, it can be well approximated by a low Schmidt rank projector. So then maybe if you have if you're taking all the rows here and you look at all their projection, then you can somehow argue that using you stack them up one against the other, that altogether they do not create too much entanglement. So it's just like a general direction. I don't have a proof of that sort, but I think it might be possible.
Further questions? If not, let's thank Itai again.
Thank you.
Session is over.